it began not with a fanfare, but with an absence, a single data point that refused to be repeated, a whisper in the cosmic noise that fell silent just as we learned how to listen. The archives of modern astronomy are vast cathedrals of light, petabytes of photons collected over decades from every corner of the sky, a record of cosmic permanence and predictable change. Yet within this orderly expanse, there exists a quieter, more elusive category of event, the transient, the anomalous, the object that appears once and is never seen again. These are the ghosts in the data, and their stories are often the most profound, for they speak not of what the universe is, but of what it might be, of the fragile threads of observation upon which our understanding hangs. This is the story of one such ghost, a planet that was and then was not, a world glimpsed in the gravitational lens of a distant star before it dissolved back into the darkness from whence it came, leaving behind only a curve of light that taunts our models and deepens the mystery of what might lurk in the great voids between the stars. To understand the vanishing, we must first understand the method of its fleeting discovery, a technique as delicate and precise as measuring the tremble of a leaf in a gentle wind from 1,000 miles away. The planet was not seen directly, for no telescope, not even the mighty James Webb, can resolve the pale blue dot of an Earth-like world orbiting another sun at interstellar distances. Instead, it was inferred through the subtle art of gravitational microlensing, a prediction of Einstein's general relativity that turns the universe itself into a magnifying glass. The phenomenon occurs when a foreground object, perhaps a star or a planet, passes almost directly in front of a more distant background star. The gravity of the foreground mass bends and warps the fabric of space-time around it, acting as a lens that briefly focuses and amplifies the light from the source star behind. For an observer on Earth, the distant star does not twinkle into a new point of light. Instead, it brightens in a very specific, mathematically predictable curve, a light curve that tells a story of alignment, mass, and distance. A single, simple lens from a solitary star produces a smooth, symmetric peak. But if the lensing star is accompanied by a planet, the gravity of that smaller world introduces a distinct, sharp anomaly, a blip on the shoulder of the larger curve, a signature that can last merely hours or even days. It is a transient alignment of perfect geometry, a cosmic coincidence that happens once and will never repeat in the lifetime of our species. The data from such an event is precious, fragile, and singular. The event was cataloged as OGLE2011BLG0421, a string of characters encoding its origin in the optical gravitational lensing experiment, the year of its detection, and its sequence in the log. For years, it resided in the vast digital repositories, one among thousands of similar microlensing alerts that scan the crowded star fields of the galactic bulge, where the density of stars makes such alignments slightly less improbable. The initial analysis, performed by automated pipelines, identified the primary lens as a likely low-mass star, a red dwarf perhaps, drifting through the interstellar medium. The light curve was complex, showing the clear, classic signature of a binary lens, not just one mass, but two. Further meticulous modeling by teams of astronomers, sifting through the data point by precious data point, revealed something astonishing. The secondary object was not another star. Its mass was far too small. The perturbation it caused was too brief, too clean. The numbers, when fed into the elegant equations of lensing physics, pointed unequivocally to a world with a mass remarkably similar to that of our own Earth, orbiting its host star at a distance that placed it squarely within the so-called habitable zone, the temperate band where liquid water could pool and persist upon a rocky surface. For a moment, in the abstract world of probability contours and chi-squared fits, an Earth twin had been found, a world of rock and potential, silently orbiting its dim sun in the galactic heart, revealed by a fleeting warp in starlight. The paper was drafted, the graphs prepared, the cautious, thrilling language of discovery assembled. And then, as is the rigorous custom of science, other teams began to look. The reanalysis is where the solid ground of discovery began to soften into the mist of uncertainty. Another group of researchers, employing a slightly different statistical model to account for the inherent degeneracies in microlensing, where multiple physical configurations can sometimes produce similar light curves, found an alternative solution. Their modeling suggested the anomaly could also be explained not by an Earth-mass planet, but by a different configuration of the source star's own motion, or a subtle, unaccounted-for binary nature in the background source itself. The pristine, singular signal began to fracture into a family of possible interpretations. The data, once so promising, was now a Rorschach test against the noise of the universe. The planet's existence shifted from a high-probability detection to a candidate, and then to a subject of intense debate. The core of the issue lies in the fundamental nature of microlensing itself. It is a non-repeatable experiment. We cannot wait for the alignment to happen again. We have one light curve, one set of photons collected over a few weeks from a specific patch of sky. And from that, we must reconstruct an entire solar system light years away. It is the ultimate forensic science, and the evidence, while compelling, is circumstantial. The planet, dubbed by some as the ghost world, began to fade not from the sky, but from the consensus. It retreated from the realm of confirmed exoplanets, back into the liminal space of unconfirmed signals. A tantalizing might have been. Its vanishing was not a physical disappearance, but a dissolution from the catalog of known things into the shadowland of scientific ambiguity, a process as quiet and inexorable as the dimming of the microlensing event itself. This retreat from certainty into the realm of tantalizing ambiguity is not a failure of science, but rather its essential, grinding engine. The story of the vanishing Earth twin is, in its quiet way, a more illuminating narrative than the straightforward discovery of 1,000 confirmed exoplanets, for it exposes the delicate scaffolding upon which our knowledge of the cosmic deep is built. We must sit with this absence, this data point that refuses to clarify itself, and ask what it means to lose a world that we never truly had, and why its ghost lingers so persistently in the halls of astrophysics. The investigation into OGL E2011BLG0421 entered a new phase, one not of confirmation, but of meticulous autopsy. Teams across the globe began to apply more sophisticated, computationally heavy techniques to the same finite set of numbers, the photometric measurements of that single background star's brightness over time. They employed nested sampling algorithms and massive Markov chain Monte Carlo simulations, not to find a single answer, but to map the vast and complex landscape of all possible answers that could plausibly fit the data. This landscape is known as the parameter space, a multidimensional territory where each axis represents a variable: the mass of the host star, the mass of the potential planet, their separation, the distance to the lens system, the relative motion. The goal is to find the valleys in this topological map, the regions of highest probability where the model light curve matches the observed data most closely. What they found was not a single deep valley representing one clear solution, but a series of ridges and plateaus, separate valleys of nearly equal depth. One valley contained the Earth-mass planet. Another, equally plausible valley, contained only stellar configurations, a dance of binary sources or subtle stellar spots mimicking a planetary signal. The data, under this more exhaustive interrogation, confessed its fundamental ambiguity. The planet was a possible story the numbers could tell, but not the only one. This degeneracy is the silent specter haunting all microlensing searches, a fundamental limit written into the very geometry of relativity we rely upon. It arises because what we observe is a two-dimensional projection of a four-dimensional event, the complex, real motion of stars and potential planets in the depths of space, flattened onto our retinal plane of the sky, and further compressed into a simple graph of brightness versus time. Information is lost in that projection. The same pattern of brightening can be produced by a lower mass object closer to us or a higher mass object farther away. This is the mass-distance degeneracy, a classic and often unsolvable puzzle without additional external clues. Sometimes, years after the event, the Hubble Space Telescope, or now the James Webb Space Telescope, can be pointed at the precise location, long after the lensing alignment has dissipated, in an attempt to detect and separate the faint light of the lensing star from the background source. If the lens star can be seen, its brightness and color give clues to its mass and distance, breaking the degeneracy. But in the crowded stellar fields of the galactic bulge, and for lenses that are intrinsically faint red dwarfs, this is a Herculean task, often yielding only upper limits, not detections. For our vanishing planet, no such subsequent observation provided a definitive key. The lensing star remained stubbornly shrouded in the glare of its neighbors and the fog of distance, its nature as elusive as the planet it may or may not host. Thus, the scientific consensus began to settle, not on a dismissal, but on a profound and open-ended notation. The signal was consistent with an Earth-mass planet in the habitable zone, but it was also consistent with other purely stellar phenomena. It was moved from the confirmed column to the ambiguous file, a place filled with the most intriguing and frustrating artifacts of modern astronomy. Yet, to leave the story there, as a mere technical footnote on degeneracy, is to miss its deeper resonance. The significance of this non-planet, this ghost in the data, extends far beyond one contested light curve. It forces a reckoning with our statistical understanding of the cosmos. The primary goal of surveys, like OGLE and MOA, microlensing observations in astrophysics, is not merely to find individual worlds, but to conduct a cosmic census to calculate the frequency of Earth-like planets around the most common stars in our galaxy, the red dwarfs. Every detection is a data point in this grand statistical calculation. But what of the non-detections? What of the ambiguous signals? If an event like OGLE2011BL G0421 is ultimately classified as not a planet, it subtly lowers the statistical estimate of how common such worlds might be. Conversely, if it is a planet, the estimate rises. The vanishing act, therefore, has a direct, if intangible, effect on our cosmic self-image. Are we one among countless Earths, or is our particular configuration of rock and orbit rarer than we hope? This single, unresolved point of light tips the scale of that answer, however slightly, toward uncertainty. Furthermore, it serves as a crucial cautionary tale for the future, for the next generation of microlensing surveys conducted from space. NASA's planned Nancy Grace Roman Space Telescope, with its wide-field instrument and location above Earth's blurring atmosphere, is designed to discover thousands of such microlensing events, including many with the signature of small, rocky planets. The legacy of OGLE2011B LG0421 will be written into the very analysis pipelines of Roman. Scientists will know to treat every initial detection of an Earth twin with a measured, quiet skepticism, to automatically and relentlessly search for those alternative valleys in the parameter space. The ghost will have taught them to look for its kin, to separate the true planetary signals from the stellar mimics with ever greater rigor. In this way, the vanished world achieves a kind of immortality, not as a place, but as a principle of scrutiny. But the narrative deepens still, venturing from statistics into the more philosophical realms of cosmology and observation. The episode holds a mirror to the nature of scientific knowledge itself, which is not a cathedral built solely of confirmed facts, but a sprawling living city with well-mapped districts of theory, bustling avenues of confirmed data, and also quiet, fog-bound outskirts where maps are tentative and landmarks shift. The vanished planet resides in those outskirts. It is a reminder that our perception of the universe is mediated through layers of interference. Earth's atmosphere, the imperfections of our instruments, the irreducible noise of the quantum world, and the limitations of our models. What we call data is never the pure signal of the cosmos. It is always that signal filtered, sampled, and interpreted. The story of this planet is a parable of that filtration process. The initial thrilling interpretation was a story we were desperately hoping to tell, the finding of another Earth. The subsequent, more sober analysis was the story the data, in all its stubborn complexity, ultimately allowed. The tension between those two stories is where real science lives and breathes. It is a slow, sometimes frustrating, but always necessary reconciliation between human hope and cosmic indifference. The universe whispered a possibility, and we leaned in close, only to find the whisper was itself composed of echoes. Yet, we continue to listen, because sometimes, amidst the echoes, a clear, soft voice speaks. To truly inhabit the mystery of the vanished world, we must leave the specific data dispute behind and journey into the broader, more haunting context. It represents the growing catalog of astronomical phantoms, objects and signals that appear with compelling clarity only to recede into the noise upon deeper inspection, leaving behind a residue of profound disquiet. These are not mere mistakes or instrumental glitches. They are the frontier phenomena, the events that occur at the very edge of our detection thresholds. In the regime where signal and noise are woven from the same thread, the vanished Earth-like planet is but one spectral member of a larger family of cosmic ghosts. Consider the enigmatic case of KIC 8462852, Tabby's star, whose irregular and dramatic dimming sparked theories from swarms of comets to alien megastructures, only for later, painstaking analysis to suggest a more mundane, if still unusual, explanation involving circumstellar dust. Or the repeating fast radio burst, FRB 121102, which for a time seemed to exhibit a precise 157-day cycle, a potential clockwork signature of a neutron star in a complex orbit, only for that perceived pattern to break and dissolve under the scrutiny of additional years of data, returning the bursts to their original state of profound unpredictability. Each of these stories follows a similar arc, an initial detection so startling it challenges existing frameworks, a period of intense speculation and modeling, and then a slow, often anticlimactic retreat into a zone of explained but unsatisfying or simply enduring mystery. The vanished planet fits this archetype perfectly, a microlensing echo of the same fundamental experience, the universe presenting a riddle that seems solvable only to pull the solution just beyond our grasp as we reach for it. This pattern speaks to a deeper, almost epistemological shift in how we explore the cosmos. We have moved from the era of mapping the obvious, the planets of our solar system, the brightest stars, the nearest galaxies, into an era of statistical inference and anomaly hunting. Our telescopes are no longer simple collectors of light. They are vast digital sieves, processing unimaginable torrents of data through algorithmic filters designed to pluck the unusual, the transient, the one-in-a-million event from the river of normality. This automated vigilance is how we find the fleeting microlensing event, the one-off fast radio burst, the anomalous light curve. But this method carries with it an inherent vulnerability. The more finely we tune our sieves to catch the extraordinary, the more susceptible we become to the subtle pathologies of our own instruments and the statistical inevitability of flukes. A single cosmic ray strike on a CCD pixel can mimic a transient astronomical event. A complex interplay of spacecraft jitter and stellar variability can create a phantom periodic signal. The human mind, exquisite pattern recognition engine that it is then tasked with interpreting these machine-selected anomalies. And it is here, in the space between the algorithm's flag and the scientist's theory, that phantoms are born. We see faces in clouds and planets in noise, The story of the vanished world is thus also a story about the psychology of discovery in the age of big data, a reminder that every signal must run a gauntlet not only of instrumental verification, but also of our own cognitive biases, our desire for the landmark discovery, the narrative breakthrough. Yet, to attribute such vanishings solely to human error or instrumental artifact is to commit a different kind of error, to prematurely close the door on wonder. There exists a more thrilling, if more disorienting, possibility that some of these phantoms are real. They may be our first, blurry glimpses of entirely new classes of objects or phenomena that reside in the gaps of our understanding, whose true nature we cannot yet comprehend, because we lack the conceptual framework to hold them. The history of astronomy is rich with such precedents. Pulsars, when first detected as the impeccably regular LGM-1, little green men, signal, were a phantom of order in the radiostatic, a pattern so precise it seemed artificially engineered. Only with the leap of insight to rapidly spinning, magnetized neutron stars did the phantom solidify into a understood, if still astonishing, reality. Dark matter itself began as a phantom, a discrepancy in the orbital velocities of galaxies, a gravitational signature without a visible source. It has refused to materialize in our detectors for decades, yet its ghostly gravitational influence is now a cornerstone of cosmology. The vanished planet, in its persistent ambiguity, could be a phantom of this profound kind. Perhaps it was not a rocky world as we know it, but something else entirely, a rogue planet, untethered from any star, momentarily aligning with a binary source in a way that perfectly mimicked a habitable zone orbit. Or a hitherto unpredicted configuration of dust and ice in a distant protoplanetary disk, lensing light in a novel way. Or even a flaw not in our data, but in the smooth application of our gravitational lensing models at such exquisite precision. It may be a messenger from a region of parameter space our theories do not yet adequately describe. This leads us to the most contemplative implication of all, the role of time and impermanence in the cosmos. Our natural inclination is to think of planets, stars, and galaxies as enduring entities, changing on timescales far longer than human history. But the universe is also filled with ephemera explosions, collisions, eruptions, alignments. Microlensing is the science of the ephemeral, a discipline built upon events that are, by their very nature, vanishing acts. The planet, if it was real, did not vanish. We simply stopped seeing its effect. It continues on its orbit, unseen, its moment of revelation past. In a universe governed by relativity and quantum mechanics, where observation is inextricably linked to the phenomenon observed, there is a poetic symmetry to a world that reveals itself only through a transient geometric coincidence and then withdraws. It becomes a cosmic lesson in humility and attention. We are forced to acknowledge that our census of the heavens is not a snapshot of a static reality, but a fragmentary collection of glimpses, a flicker book of the cosmos where most pages are blank. The vast majority of Earth-like planets in the galaxy will never betray their presence to us through transit or microlensing. They will orbit in perpetual silence, unseen and unknown. Our vanishing world, then, is a symbol for all those unseen worlds, a single data point that flickered into our awareness long enough to remind us of the overwhelming, silent majority that does not. The contemplation of silence and unseen majority naturally draws us inward, from the galactic scale to the human scale, to consider the instruments and the minds that captured this phantom in the first place. The story of the detection is as much about the quiet, relentless vigilance of automated surveys as it is about the elusive signal itself. The optical gravitational lensing experiment, OGLE, operates from the Las Campanas Observatory in the clear, dry air of the Chilean Andes. Its telescope, a humble workhorse compared to the giant segmented mirrors of modern observatories, yet its contribution to time-domain astronomy is immeasurable. Night after night, for over 3 decades, Its camera has stared at the same dense star fields toward the center of our Milky Way, taking image after image, measuring the brightness of hundreds of millions of stars. This is not the flashy work of pointed observation, but the deep, rhythmic pulse of a survey, a cosmic monitor recording the vital signs of the galaxy. The data stream is a river of numbers, flowing into servers in Warsaw, where algorithms in real time perform the unimaginably tedious task of comparison. They subtract last night's image from tonight's, looking for the subtle changes that betray a microlensing event in its earliest stages. One star among millions, beginning an almost imperceptible climb in brightness. The system is designed to catch the gentle rise of a standard event, but its true value lies in its sensitivity to the anomalous, the unexpected bump on the curve. It was in this river of data, amidst the flow of thousands of confirmed lensing events, that the unique signature of OGLE 2011BLG0421 was first flagged not by a human eye, but by a line of code executing a conditional statement. The planet's first whisper was to a machine. This handoff from silicon intuition to human interpretation is the critical juncture where mystery is either born or resolved. The alert went out across the global network of microlensing astronomers, triggering what is known as a follow-up campaign. Other telescopes, part of collaborations like MOA in New Zealand and the Microfund network spanning continents, swiveled to train their lenses on the same patch of sky. This was not to take a prettier picture, but to gather more data points, to densify the light curve, to capture the precise shape and timing of the anomaly with a fidelity the survey telescope alone could not provide. Every additional photon was a precious constraint, narrowing the possibilities. The observers, often graduate students and postdoctoral researchers working through the night, were gathering the raw material for a story whose ending they could not know. They were measuring the depth and width of a ghost's footprint. The data from these follow-up observations is what ultimately created the detailed, multi-peaked light curve that held such promise. It provided the crucial coverage of the planetary deviation, the blip that lasted perhaps a day or two. Without this globally coordinated, human-driven response to the machine's initial alert, the event would have been just another smooth curve in the archive, its complexity lost to undersampling. The phantom was given form by this chorus of telescopes, a shape detailed enough to inspire both hope and, later, rigorous doubt. It is a profound reflection on modern science. The discovery is automated, but the understanding, the slow, often painful reconciliation of expectation with evidence remains an intensely human endeavor, conducted in conference rooms and over late-night emails, fueled by coffee, and a stubborn refusal to let an interesting signal go unexplained. And so, the data traveled from the Chilean mountaintop, through pipelines in Warsaw, to the desks of modelers in Ohio, Japan, and France. These are the cartographers of parameter space, the ones who take the raw photometry, the list of times and brightness measurements, and attempt to reverse engineer the celestial mechanics that produced it. They work with families of mathematical models, each a set of differential equations describing the relativistic bending of light around 1, 2, or more masses in motion. Their computers perform billions of iterations, tweaking the model parameters minutely each time, searching for the configuration that best fits the observations. The output is not a simple answer, but a probabilistic landscape, a map of likelihoods. When they first mapped OGLE 2011 BLG0421, they found a prominent, compelling peak at the location of an Earth mass planet. It was a clear hill on the map. The initial papers, written with the cautious optimism required of the field, described this hill. But as is the custom, other cartographers, using different mapping techniques or starting with different prior assumptions about the population of stars in the galactic bulge, began to survey the same territory. They found that the landscape was more treacherous than it first appeared. What looked like a single, dominant peak was, upon closer inspection, connected by a high ridge to another, separate peak in a different region of the map, a region that corresponded not to a planet, but to a stellar binary source with a certain orbital configuration. The two solutions were, in the technical parlance, degenerate. The data could not distinguish between them. The clarity of the initial discovery gave way to the fog of ambiguity. The modelers, in their quiet offices, were not debunking a discovery so much as they were revealing the intrinsic limitations of their own maps, the places where the terrain of theory was not yet resolved finely enough to show a single path. The planet began its vanishing act, here, in this abstract, multi-dimensional space, fading from a high-probability location to one of several plausible coordinates. This process exposes the beautiful and sometimes heartbreaking iterative nature of scientific knowledge. The first model is almost never the final one. It is a hypothesis cast in mathematics, fitted to data. It is then stress tested by the community, pulled and stretched, examined under different lights and from different angles. The models for microlensing are extraordinarily sophisticated, but they contain within them simplifications and assumptions about the smoothness of the source star's surface, about the unblended light from other stars in the crowded field, about the uniform motion of the lens system across our line of sight. The subsequent reanalyses of the vanishing planet probed these very assumptions. What if the source star had a large, dark star spot that rotated into view during the event, subtly altering the shape of the brightening? What if there was an unseen, very faint star blending its light with the source, skewing the measurements? Each of these what-ifs generated a new family of models, a new exploration of the parameter space. Some of these explorations found viable fits that did not require a planet. With each new plausible alternative, the Bayesian probability, the mathematical expression of confidence associated with the planetary solution, dwindled. It was not disproven, it was simply surrounded by equally viable alternatives. Its stature diminished through a process of contextual dilution. The scientific literature tells this story in its dry, technical language. We find two classes of solutions, or the planetary interpretation is degenerate with a source binary model, or further, high-resolution imaging is required to break the degeneracy. But beneath that language lies the narrative of a world slipping away, not in a flash, but through a slow, meticulous erosion of certainty by the very tools we build to create it. The fading of the planetary signal from a high probability detection to a contested ambiguity leaves us not at an end, but at a threshold, gazing into a future shaped by the very questions this ghost has raised. The legacy of this non-discovery is paradoxically more active and formative than that of many solid confirmations, for it directly informs the next generation of explorers and the design of the tools they will use. The central lesson is one of humility in the face of cosmic complexity, a lesson now being encoded into the silicon and software of forthcoming missions. The Nancy Grace Roman Space Telescope, slated to launch later this decade, represents the apotheosis of the microlensing method, a space-based observatory dedicated to performing a galactic exoplanet census, free from the blurring effects of Earth's atmosphere. Its core mission is to find hundreds of Earth-like planets via microlensing, to finally answer the statistical question of how common our world is. But the scientists planning its mission are now acutely aware of the ghosts in the data. The analysis pipelines for Roman are being built with the story of OGLE2011, BLG0421, and its kin etched into their logic. They will automatically, from the very first alert, perform exhaustive searches for degenerate solutions. They will employ machine learning algorithms trained not just on idealized models, but on the messy, ambiguous events from ground-based surveys, teaching the machines to recognize the subtle hallmarks of a stellar mimic or a binary source degeneracy. The vanished world, in its elusiveness, is thus a silent collaborator on the Roman mission, a cautionary benchmark against which all future candidate Earth twins will be measured. Its existence as an unresolved case study ensures that the threshold for confirmation will be higher, the scrutiny more relentless, and the final catalog of discoveries correspondingly more robust. This forward-looking perspective also shifts the focus from the specific, lost planet to the population it might represent. Microlensing is uniquely sensitive to planets at orbital distances, akin to those in our own solar system, including the colder, outer regions where other methods struggle. It is also the primary method for detecting free-floating planets, worlds untethered to any star, drifting through the interstellar dark. Could the vanished signal have been an extreme version of such an object, a rogue Earth, momentarily aligning in such a way that it mimicked an orbit? The models allow for this, though the probabilities are even lower. This line of thinking expands the mystery from, was it a planet, to, what could it have been? And in doing so, opens doors to more speculative, yet physically possible realms. The field of theoretical astrophysics is populated with such shadow objects, ancient black holes from the early universe, condensed knots of dark matter, exotic phase transitions in the vacuum of space. While Occam's razor favors the more mundane stellar explanations, the mere possibility that a subtle light curve could be our first hint of something truly unknown is a powerful motivator for continued, careful observation. The ghost becomes a placeholder for future discovery, a marker in the data that says, here, something not fully accounted for occurred. It invites a deeper listening, a more patient attunement to the frequencies of the cosmos we have not yet learned to properly hear. On a more philosophical plane, the episode holds a mirror to our own place in the universe and the nature of scientific progress. For centuries, astronomy was the science of the fixed and permanent, the immutable sphere of stars, the clockwork regularity of the planets. The modern era has revealed a cosmos of dynamic violence and constant change, exploding stars, colliding galaxies, evaporating atmospheres. But the vanished planet introduces a different kind of change, epistemological transience. It represents knowledge that flickered into being and then retreated. This is unsettling because it challenges the linear narrative of scientific advancement, the idea that we are steadily filling in a map that becomes ever more complete and accurate. Instead, it suggests the map has regions that appear solid under one light, but become indistinct under another, that our understanding can, in localized instances, lose resolution as easily as gain it. This is not a flaw, but a feature of probing the limits of detection. The frontier is always fuzzy. The vanished world exists in that frontier fog, and by doing so, it honestly represents the state of our knowledge at the bleeding edge, a state of productive, pregnant uncertainty. It tells us that the universe is not merely hiding its secrets in darkness or distance, but sometimes in plain sight, disguised as something else, leaving us with the profound task of discernment. Thus, we return to the silent patch of sky near the galactic bulge, the coordinates of O, G, L, E, 2011, BLG 0421. Nothing distinguishes it to the eye, or even to the most powerful telescope. The background star shines on, oblivious. The lensing star, a faint red dwarf perhaps, continues its slow journey along the galactic plane. If a planet is there, it completes orbit after orbit, its surface bathed in the dim, ruby light of its sun, a world of mountains and valleys, of possible oceans and skies, forever silent to us. Or it is not there at all, and the anomaly was just a fleeting dance of stellar shadows. We may never know for certain. This is the essence of the story. Not a discovery, but a lingering question. Not an answer, but a sustained note of mystery. In a culture often obsessed with definitive conclusions and groundbreaking announcements, the tale of the vanished planet is a necessary counterpoint. It is a narrative of the pause, the ponder, the unresolved. It celebrates the search itself, the meticulous gathering of photons, the crafting of models, the community debate all in pursuit of a truth that remains, and may always remain, just out of focus. The planet's greatest gift is not the thrill of its tentative discovery, but the deep, quiet humility of its loss. It teaches us that the cosmos is not only a repository of wonders we can find, but also of wonders we can almost see. Ghosts in the data that remind us of the infinite complexity lurking just beyond the edge of our understanding, compelling us to keep looking, to keep listening, to keep wondering at the soft, elusive whispers of the real. In the wake of the unresolved, we are left with the enduring echo of the event, a resonance that travels beyond the immediate circle of microlensing specialists and into the broader cultural and philosophical contemplation of our place in the cosmos. The vanished planet, this Earth-like ghost, becomes more than an astronomical case study. It transforms into a modern myth, a narrative vessel for our collective hopes and anxieties about other worlds and our own solitude. For a brief, luminous moment in the scientific literature, humanity had a candidate, a possible twin, a rocky sphere in the temperate zone of another sun. The psychological impact of such a prospect, even a tentative one, is profound. It touches upon ancient questions of uniqueness and companionship in the universe. Are we alone? Is Earth a singular masterpiece of fortuitous conditions, or is it a common template, repeated on countless worlds spun from the same galactic dust? The initial detection offered a whisper toward the latter, a hint of cosmic fertility. Its subsequent ambiguity, however, does not simply return us to square one. Instead, it leaves us in a state of suspended animation, a Schrodinger's cat of a planet, simultaneously existing and not existing in our collective consciousness. This state is arguably more evocative, more creatively and intellectually fertile than either a firm yes or no. It holds the door to possibility ajar, allowing the chill wind of the unknown to keep us alert and wondering. This cultural resonance finds expression in the arts and in the public imagination. A confirmed Earth twin becomes a data point, a statistic for textbooks. A vanished one becomes a story. It is the stuff of science fiction, not as a cliché, but as a deeply rooted speculative premise. The world that was there and then gone, the deciphered signal that cannot be reacquired, the artifact that dissolves upon examination. It speaks to our fear of ephemerality and our longing for connection in a vast, indifferent universe. The phantom planet joins a lineage of such motifs, from the disappearing islands of ancient mariners' maps to the canals of Mars perceived by Lowell. Each represents a projection of human desire onto the blank screen of the unknown, followed by a recalibration of reality. But unlike those purely illusory visions, this one is grounded in the impeccable logic of general relativity and the precise, unsentimental language of photometry. Its power derives from this duality. It is both a rigorously derived scientific datum and a profound existential riddle. It is a reminder that our most advanced tools of discovery do not eliminate mystery. They simply relocate it to a higher, more sophisticated plane, trading folklore of sea monsters for the tantalizing degeneracies of Bayesian statistics. On a practical level, the case has cemented a new standard of caution in exoplanetary science, particularly for claims of rare or landmark discoveries. The peer review process for such papers now demands, as a matter of course, an exhaustive treatment of alternative models and degeneracies. The burden of proof has been invisibly raised by the collective memory of events like this one. When the James Webb Space Telescope turns its gaze to the atmospheres of distant worlds, searching for biosignatures, the molecular hints of life, the specter of the vanished planet will be there too. A tantalizing whiff of oxygen and methane on a temperate world will not be announced as the discovery of life. It will be presented as a compelling signal, followed immediately by a dissection of possible abiotic mechanisms that could produce it, from photochemical processes to geological outgassing. The scientific community has learned, through experiences etched in data, like that of OGLE 2011 BLG 0421, to savor the discovery process itself, to dwell in the meticulous, slow work of validation, and to resist the siren call of a premature narrative. This learned patience is a form of respect for the complexity of the universe, for the rigor of the method, and for the public's trust. The Vanished World taught that the most ethical and profound way to share the journey of exploration is to share its uncertainties alongside its triumphs. Looking forward, the mystery may yet see a form of resolution, though not the kind we might initially hope for. The Nancy Grace Roman Space Telescope will not reobserve the same event. That alignment is lost to time, but it will create a statistical context so rich that the nature of such ambiguous signals may become clearer. By detecting thousands of microlensing events, Roman will allow scientists to build a precise understanding of the background, the intrinsic rates of stellar variability, the frequency of binary source stars, the common artifacts in the data. Against this new, exquisitely detailed backdrop, the singular anomaly of the vanished planet can be re-evaluated. Was it a 1 in 100,000 statistical fluke, now recognizable as such? Or does its light curve shape appear again and again in the Roman data, a signature finally recognized as belonging to a new, distinct class of object? In this way, the ghost may find its place not as a solitary mystery, but as the first known member of a population. Its legacy will be fulfilled not by being confirmed as a planet, but by serving as the Rosetta Stone for deciphering a whole category of phenomena we currently cannot name. Its value lies in its persistent question mark, a question that will guide sharper inquiries for decades to come. And so, we are left with a quiet testament to the nature of exploration at the boundaries of knowledge. The story of the Earth-like planet that vanished from our data is not a tragedy of error, but a quiet epic of careful seeing. It encompasses the automated vigilance of a telescope in Chile, the global network of follow-up observers, the late-night toil of modelers mapping abstract landscapes, and the solemn, collective deliberation of a scientific community weighing evidence. It is a story that honors the signal while rigorously interrogating it, that embraces the initial thrill of possibility without succumbing to it. The planet, whether it is truly out there or not, has performed a vital function. It has stretched our methodologies to their limits, exposed the soft boundaries of our understanding, and reminded us that the universe communicates not only in shouts of supernovae and the grand spiral choreography of galaxies, but also in the faintest of whispers, so easily mistaken for silence. In the end, we are not poor for having lost a world from our catalogs. We are infinitely richer for having honed our ability to listen, for having learned to sit, comfortable yet alert, in the vast and humbling space of not knowing, where the next whisper, perhaps clearer than the last, is always just about to begin. The final contemplation of this vanishing leads us inward, to the most intimate frontier of all, the human mind grappling with the sublime scale and silence of the cosmos. The ghost planet is a psychological artifact as much as an astronomical one, a reflection of our cognitive apparatus straining to find patterns, assign causes, and weave narratives from sparse and uncertain data. This struggle is not a weakness of science, but its very engine. It is the friction between raw observation and understanding that generates the heat of discovery and the light of insight. When we look at the light curve of OGLE 2011 BLG 0421, we are not seeing a simple graph. We are witnessing the output of a vast, unconscious cognitive process. A process that begins with the retina of the CCD, flows through layers of software designed by human minds to highlight deviations from the norm, and culminates in the conscious, deliberate act of a researcher leaning toward a monitor, their intuition sparked by a subtle inflection in the curve. That moment of recognition, the "this is interesting" moment, is a leap across an abyss of noise. Guided by years of training, and an internalized model of how the universe should behave. The initial planetary interpretation was a story the mind yearned to tell because it fit a beautiful, pre-existing narrative. The Copernican principle, the idea that Earth is not special, that what exists here must exist elsewhere. The subsequent, more ambiguous interpretations were stories the data, under duress, was forced to concede. The entire episode is a microcosm of the scientific dialectic, played out in the domain of photons and probabilities. This cognitive journey mirrors a deeper, almost existential process of mapping the known onto the unknown. We have only one reference point for a habitable world, our own. Every model for an Earth-like planet, every definition of a habitable zone, every imagined biosignature molecule is an extrapolation from this single data point. When we find a signal that seems to match that template, the temptation to complete the picture, to populate that world with mountains, oceans, and perhaps even life, is almost irresistible. It is a form of cosmic pareidolia, seeing a familiar face in the random contours of a distant, blurry image. The vanished planet case is a powerful corrective to this instinct. It forces us to hold the template lightly, to remember that Earth-like is a category we have invented, one that the universe may fill with objects that only vaguely resemble our prototype or that exploit loopholes in our definitions we have not yet conceived. The planet's fade into ambiguity is a lesson in intellectual flexibility, a training in how to think about things that defy easy categorization. It prepares us for the truly alien discoveries that may lie ahead, discoveries that will not fit neatly into the boxes we have prepared. In this light, the field of exoplanet science itself can be seen as a grand collective exercise in overcoming these cognitive biases. The Kepler mission taught us that planets are more common than stars. TESS is showing us the dazzling variety of planetary systems, many of which look nothing like our own orderly solar architecture. Microlensing probes the colder, more distant orbits where other methods are blind. Each new method and mission is a new sense organ, allowing us to perceive different aspects of the planetary population. The ambiguous signals, the ghosts, the one-off anomalies. These are the stimuli at the edge of our perception, the peripheral visions of our new senses. They are the data that doesn't yet make sense. Paying attention to them, as the scientific community did with this microlensing event, is the equivalent of training our eyes to see in the dark, or our ears to hear a wider range of frequencies. By sitting with the discomfort of the unresolved, we expand the very capacity of our scientific consciousness. Ultimately, the story of the vanished planet brings us to a quiet, humbling acceptance of the limits of knowledge, not as a barrier, but as a horizon. There will always be signals that sit on the threshold of detection, events that occur once and are never repeated, objects whose true nature remains just beyond the reach of our best instruments and brightest minds. This is not a failing. It is a fundamental characteristic of exploring a universe that is vaster, older, and more complex than we can fully comprehend. The acceptance of this limit is what separates mature science from naive optimism. It allows us to pursue answers with fervor, while holding them lightly, once found, always open to revision, always aware that today's discovery may be tomorrow's ghost. This philosophical stance is the greatest legacy of episodes like this one. It cultivates a scientific temperament that is both passionate and patient, bold and humble, forever curious but never arrogantly certain. Thus, we return one final time to the coordinates in the galactic bulge. The star shines on, a point of light among billions. Our data, our models, our debates are but a fleeting whisper in the billion-year history of that system. Whether a rocky world orbits there or not, our engagement with its possibility has changed us. It has refined our tools, sharpened our questions, and deepened our appreciation for the delicate art of listening to the cosmos. The planet may have vanished from our data, but in its vanishing, it has left an indelible imprint on our method and our mindset. It stands as a silent monument to the beauty of the search itself, A search conducted not with the expectation of easy answers, but with a reverence for the profound and elegant mystery of a universe that reveals itself slowly, in fragments and whispers, always holding something back, always inviting us to look again, to listen more closely, to wonder more deeply. In the grand, slow narrative of cosmic discovery, such ghosts are not interruptions. They are essential verses, reminding us that the poetry of the universe is often written in the spaces between the words, in the silence between the notes, in the luminous, unresolved questions that guide us ever onward into the dark.